My name is Stefan Bogenhauser, Product Manager for Displays, and I'd like to welcome you for today's webcast about display technologies. So what I brought with me for the next roughly 1 hour is I'd like to give you an overview about currently existing different display technologies, how do they work, what are benefits, what are restrictions, and what are they used for. Then I want to dive into a little bit deeper into the LCD technology, because this is a dominating technology nowadays. Discuss a little bit difference between technologies, TN, PVA, IPS. I also would like to have a look on backlights for LCD displays. LED currently is everywhere in the speech. And then I also have some items that are not panel related. Panel is not all in a display, but there's also something around it. For example, interface, DisplayPort, HDMI interface, what it is good for, where is the focus. Overdrive technology, this is something to make displays very fast, response times of 3 milliseconds. How can they be realized? And at the end of the presentation, there is the question, how can LED backlight make millions to one contrast? What means static contrast? What is dynamic contrast? And how is it realized? So let's start with the technology overview. So I put together different technologies, and let me start with technologies that are so-called B-stable technologies. What means B-stable? B-stable means, for example, when it's white, the pixel is white, it doesn't need energy to keep white. It only needs energy to be switched from white to black. But if it's then black, it also doesn't need energy anymore. One example of this, which is well known, is the electronic ink or electronic paper. What is the principle? You see here in the picture, on a layer, on a very thin layer, there are small microcapsules which are filled with a liquid, and in this liquid there are black and white parts swimming. These are loaded, positive or negative. So if the loading is positive on the bottom, negative on the top, the pixel is black. Now a short impulse of voltage is enough to turn this around, and suddenly the pixel is white on the top where the user sees it and black on the bottom. So the pixel is switched from black to white. To hold this state, you don't need energy anymore. With another voltage impulse, it can be turned back again. It's not only possible to make it black or white. When using color filters, it's also possible to display colors with this technology. The advantage is you can realize a very high resolution because the capsules are very small. It takes very low power if the picture is not switched too often. Color is possible, and it can be very thin and even flexible. You see an example here. A small display, a flexible display can be banded, can be put on curved surfaces. The restrictions of this technology is clearly the refresh rate. So it takes quite a long time to switch from one pixel to another, from one state to another. So it's not good for videos or for zooming the content. Also a restriction is so-called ghost images. Means if you switch to another page, for example in an electronic reader, you still see a light picture of the former one. So it takes special electric circuits and changes of pixels to make this disappear again. The usage of this technology is clearly in electronic readers, PDAs or electronic readers, for videos, displaying videos, or using it on a desktop in office applications. It's too slow and the capabilities of displaying colors and contrast is too low. So especially for electronic readers. Let's go to the next page. Shortly mentioned two other B-stable technologies. The electrochromic technology is using chemical reactions. The principle is you move with electric voltage substances to the one or to the other side, and on each side there is a chemical reaction with the other substances here. And these substances are chosen so that they change the color. So if, for example, if the reaction is on this side, it's getting dark. If it's on the other side, it's getting bright. This is a very energy-saving technology, but quite poor in colors. You can only display two colors and only a quite rough resolution. So the typical application for these technologies is like shown in the picture, for example, a label in a shelf of a store. So there where you former stick paper labels, you can use this electronic one, and nobody has to go around and change it. If prices change, you can give the information from the server and it does it automatically. Another quite similar technology, similar in the usage, is called electrowetting. Wetting has something to do with liquids, and indeed they are using liquids. They are using water and a colored oil. Oil and water does not mix together, so the oil in this side covers the whole pixel. The oil is colored, for example, blue in this example, so the whole pixel is blue. If now there is an impulse of voltage, suddenly the oil comes together, getting a higher bubble, and only covers a small part of the pixel, and most part of the pixel is no more color of oil, but the color of the background. So also a very simple, very energy-saving technologies, but with poor color, only two colors possible, and very low resolution, so application is quite the same. It is either in shelves of stores, or it also used sometimes in industrial applications. For example, here there's a little watch here. You can read the time here. So very simple displays, but cheap displays, very robust displays, and very energy-saving displays. But also in future, no application in office use or in TV sets. Let's go to the next one. This is a quite interesting one, also a B-stable, meaning energy-saving technology, called IMOD, I standing for interferometric modulation. This uses small membranes which are mirrored, and this membrane, this one that is here at the top of this arrow now, has a distance to the surface which is only in the range of a micrometer, 1 million of a meter, 1 million parts of a meter. So very small distance, and this is needed because the distance must be in the length of the wave of the light. And the principle is that this membrane can be switched by current, by voltage, from one stage to another stage. And the distance between the surface and the membrane is switched from half of a wavelength of the light to quarter of the wavelength. What does this affect? It affects that it switches from a constructive interference, meaning the reflected light of the membrane is exactly at the wave of the reflected light of the surface of the panel. And if it's switched in the other distance, it's a destructive interference. That means the wave is exactly opposite and deletes the light of the reflecting surface of the panel. So this is possible with very small distances of the whole panel. It's quite easy, it's quite robust, but you can imagine that to produce this is quite a challenge. So it's really nanomechanic to produce this. Colors are possible, but each color has another wavelength. So the distance of red, for example, is the highest distance. The distance of green is lower, and the distance of blue is the lowest because wavelength of blue light is lower than red or green. The advantage of this display is very low power consumption, very fast response times. So it's quite 1,000 times faster than an LCD display. So for example, different colors can be made by dithering, by switching on and off in very fast and such, so mix the color. It is also readable by sunlight because it only makes light by reflection. There's no backlight here. The contrast is not so high, so 15:1 is currently possible. And if you use it in a room, you need an external light source, which of course needs energy again. So this is a technology that currently is used and will be used in future in outdoor devices, for example, GPS devices. The company Mirosol has already commercialized the first small devices. You see here a small reader. So it's really a technology that's coming up, but it's coming up not on the office desk. It's more coming up for small devices for outdoor use. So now we leave the B-stable and energy-saving technologies and come to another kind of display technologies. Plasma technology is quite old technology, but still in large-size TV sets or digital signage monitors. How does it work? Here it's cut off. So these cells, these color cells, are the plasma cells, and these are small cells that really produce light. It's some kind of like a light tube, fluorescent tube. Each pixel is divided in 3 parts. So per pixel you really have one red, one green, and one blue lighting element. You have the electrodes to get power on it, and there is a glass plate on front, and there is another plate on the rear side to mount all these things. The advantage is it has really brilliant colors. It has a deep black and high contrast because if the element is switched off, it is really black. It has an ultra-wide viewing angle because it's not using any polarization filters, and it's very fast in the response time. So perfect for brilliant pictures, for TVs, for moving pictures. However, there are also some quite heavy disadvantages. For example, the energy. So it's using a lot of energy, even so much energy that if you display a white picture, you have to reduce the brightness because otherwise it would get too hot and the energy consumption would be too high. It has heat problems, especially if it comes to a small dot size. That's why it's often used for large screens, but never came on an office desk because the resolution, the dot size would be too small, and it's also quite heavy in design. It has mostly metal frames that are able to hold all these things. Burn-in problems, especially for digital signage systems. You have to refresh a picture from time to time, otherwise you always see the picture that was standing before you change it. So use it in large TV sets and digital signage. Another technology that also uses lighting dots is so-called OLED technology. You might have heard about this. It's coming up even more often. And just today I saw that one company now announced a even 24-inch OLED display. How does it work? Or where does the name come from? Let's start with this. LED is clear, it's light emitting diode, and the O in front of is for organic. Why organic? Because the layer where it's put on is organic material. This is from the production process. So there is a plate where it's mounted on, then there is the TFT array, then there is the organic layer which includes the LEDs, and then there is the cathode layer for the other pole of the voltage. When you look onto it, this is an example of the matrix. You see there is red, blue and green dots on it. So you really have small LEDs in these base colors sitting on a special pattern. The pattern shows different sizes. Why different sizes? Because blue, for example, needs larger size to have the same intensity of light than for example, the green one or the red one. So this is an example of the matrix, how it is used currently in display devices. Each of these points is really emitting light, so also no polarizers. That means a very wide viewing angle. The advantages is high contrast. High contrast because it also produces a very dark black, because if it's switched off, it's really dark. It's auto readable. Power consumption is low, but it is only low if you show a dark background. Why? If you show a white background, all the LEDs are bright and the power draw is even 3 times higher than LCD. But if you show a picture, colored picture, it's already below about 80% of LCD with this example. And here is an example of a current mobile phone, which mostly have a black background, and with the black background you reduce dramatically the power draw, and it comes down to only 40% of a comparable size of LCD. So the content must fit also to this technology. Office content more looks like the white one, black characters on a white background. So OLED for office is not the best choice. It's a better choice for mobile phones, for devices that show colored pictures. Response time is very fast. So response time is much faster than the LCD, so it's perfect for moving picture. It can be produced very thin and even on flexible layers. So flexible displays are possible. And I already mentioned it's a very wide viewing angle because no polarizer films are used there. The disadvantage is that it works very well with small devices, because small devices can use passive matrix. Larger devices need active matrix. Active matrix means that each pixel needs TFT device, TFT circuit to keep the information until the next refresh is coming. And this active matrix makes OLED currently very expensive and very complicated to produce. So OLED currently more focused on the small devices. Also a restriction is the lifetime, especially the lifetime of the blue color is much shorter than the other ones. So if you want to show consistent color, you even have to adjust the color during the life cycle. Sticking image is an issue, especially on these passive matrix displays. And the power consumption with the bright background already mentioned, this is, for example, needed in office use, is also higher than LCD, so it's not the best choice for the office use. Used in, for example, in photos or in mobile phones. Yeah, let's come now to the LCD technology, which is currently really the dominating technology, and especially when it comes up to office monitors, it's really the dominating one, and also will be the dominating one for the next years. How does it work in principle? LCD technology needs a backlight sitting on the rear of the display. This backlight, and in front of this backlight, there is the LCD module. This one, these different layers in total are only about 2 millimeters thick. This is a small plate visible as a glass plate in front of the thicker backlight. The LCD modules, the liquid crystals, are sitting in between, and in total you have different layers. For example, the glass plate on the rear side, one glass plate on the front side. This is for mechanical adjustment of everything. Then you need electrodes, lines and columns to be able to give the power to each and every pixel. Then you have so-called alignment plates. Alignment plates bring the LCD modules in the right direction. If there is no power, then they fall into this small structure of the alignment plates, and if they get power via the electrodes, then they move here. They move out of the alignment plates, they change the position, and with changing the position, they change the flowing of the light here. The flowing of the light, you need the polarization filters on the rear side and on the front side. If the light is flowing straight through, it doesn't come to the filter on the front side because it has another direction than the one on the rear side. But if the liquid crystals turn the light by 90 degrees, then it goes through the front filter and you have the pixel bright. So the task of the LCD, of the liquid crystals, is, depending on the voltage, to turn the light in a way that the right brightness for the pixel is coming up to the front. How is color made? Here you see the color filters. So each pixel is divided in 3 subpixels for each of the basic colors. These are so small that the human eye doesn't see the single color, but only a mixture of the whole picture. So if you display red, you only open the red one, you close the other ones, and so you can mix up to 16 million colors or even 1 billion colors with our P27. So this is basic how it works. Let's look now at this LCD module and have a look on the 3 different currently existing technologies, how the LCD module can be produced and what are the benefits out of it. The simplest one to produce a display is a so-called TN, twisted pneumatic technology. Here the movement of these LCD modules is quite simple. So they turn in a very simple way, they need less energy to turn. However, you cannot control so exactly the flow of the light. The other technologies have a more complex kinematic, a more complex moving of these LCD modules. This makes it more expensive, but the control of the light flow is much better. You see this, for example, in the viewing angle. The viewing angle of this IPS and VA technology is much higher than the one of TN. I forgot one thing. The name of this IPS, for example, gives already a hint of the different kind of movements of these LCD modules. IPS is the abbreviation for in-plane switching. So the LCD molecules are switching in one plane, while VA, the letters VA can be in PVA or MVA. This is quite similar. VA is the abbreviation of vertical alignment. That means the LCD module, if they are not powered, they are vertical aligned, standing vertical to the display surface. So the difference of the technologies is simply the movement of these LCD molecules. So coming back to viewing angle. Viewing angle is something standing in the datasheet, but what it's more important for the quality of the picture is the next two items. It's color shift and color balance. Color shift means if you look from the side, how keep the color, how constant keep the color. For TN, you lose very fast the colors, but for IPS and VA, they keep stable for quite a while for a wide viewing angle. We will see this on the next slide. Color balance is something that has to do with how exactly the color can be displayed. So the movement of TN is not controllable so well, so the color balance is good enough for office applications, but in some high-end applications like CAD or picture publishing, this is not good enough, and here is the advantage of the IPS or VA panel. Next items are response time. Response time on-off. So if you switch from a very dark to a very bright pixel or back again, this is the advantage of TN. They are very fast. IPS VA are slower because more LCDs have to be moved, and this takes more time. However, there is a technology overdrive. I will come to this in the next slide. And with this technology, you can make very fast so-called gray-to-gray response times, also in the high-end technologies. And this is very important for displaying, for example, CAD modules, moving it on the screen, or making fine rendered parts and display it on the screen. The big advantage of TN is, of course, power consumption and the cost, because it's quite easy structure. Power consumption for an IPS and PVA was much higher, and in some cases still is much higher, but there's upcoming LED technology. It is good enough even now to make the first IPS sizes out of it. And we have this 23-inch already in IPS with LED backlight, and here we could reduce the power draw also for the high-end panel, and this will coming up in the next years or two. So maybe next year or in 2 years, the green bars will also be in VA and IPS, but nowadays most of these high-end panels take quite more energy than the TN. Also, cost isn't different. So cost is between 30 and 50% more the cost for the panel itself, because production is more complex for the high-end panels. So the applications, TN is perfect for office applications. It's also perfect for gaming. One people sitting in front of the screens, colors is not so critical. You can save money, you can save energy. So we use it in most of our lines, business, E-lines, SL lines, also for entertainment. But there's also applications for the high-end panels, like graphic applications, desktop publishing when it comes to colors, multi-monitor use. If you have more than one monitor in front of you, you need a wider viewing angle, or if you put it to pivot orientation. This is the use case for the high-end technologies, and we and a lot of competition offer this in the premium line, professional lines, premium lines. So I already said to you in the last slide that color shift is one of the very important differences between TN and IPS or PVA. This shows TN example on the left side, and IPS example, PVA, is quite similar on the right side. What does it show? It shows so-called gamut. Gamut is a kind of measurement of the capabilities to show the colors of a display. It was defined 100%. Trinitron TV set years ago was defined as 100%, And related to this Trinitron TV set, CRT type, most of the TN panels are able to display 75% of colors. This is a standard today. And you see here, so in the middle is 0 degree. What means 0 degree? You look straight right angle to the display. And if you go up and down and also on the side, this is the viewing angle, the deviation from the vertical viewing direction. So for TN panel, if you go 40 or 50 degrees on the side, the loss of the color gamut is already about 10%. And 10% is a value where you see the human eye sees dramatic changes in the color. The color even invert. Suddenly you see green instead of red or something. And this happens very soon on the TN panel. Again, if you alone sit in front of your desk and you don't need very good colors, only make office application, this is good enough. But if you work with colors, or if you look more from the side, for example, more users looking to a presentation, the IPS or PVA panels have a much more constant gamut over the whole viewing angle. So here it stops, it's about 85 degrees. You can't see it because of the frame of the display. But you see the colors won't change over a very wide viewing angle, and this is big advantage of this IPS and PVA, especially when it comes to colors and to presentations to large screens where you need the good viewing angle of the display. So now we looked at the LCD module itself. Let's come now to the backlight, the second element of a LCD display. Just showed here a little bit history, how it developed. So about 2 years or 3 years ago, we used so-called CCFL, cold cathode fluorescent lamps. These are lamp tubes like they are used in the office to make the light in the office. You see these lamps here. We opened the 26-inch monitor. We took away the LCD module, so you see into the backlight. And these stripes here, these are the CCFLs. These are the tubes that make the light. You need a lot of them because otherwise you don't see a homogeneous brightness, but only bright stripes and dark stripes on the display. And you need a quite huge distance, which is the thickness here, to spread the light over the whole screen. So the old screens were quite thick, quite heavy, and with a lot of lamps, they used a lot of energy. 1.5 years ago, in October 2009, there was a new Energy Star released, and this new Energy Star roughly cut the energy limit to half. So it was not possible anymore to realize this Energy Star with this kind of technology. So what did industry do? They reduced the amount of lamps to the half, so they used 4 or 2 lamps in future, and they put the lamps on the side, on the left and on the right side. And to spread the light, they used a light guide, which is a glass plate, which is mirrored on front, on the rear side, and distributes the light over the whole screen. And this opened the way for the LED backlight, because LED has a very small cone of light. It is not possible to make this kind of direct blue, but if you put it on the side, here you see a picture of the LED module. This is the LED bar. These dots are the LEDs. They put the light into the glass plate. You see it here. This mirror of the hand is a glass plate, and this glass plate distributes the light over the whole screen. Let's have a look on the next slide a little bit more in detail how it works. So here this is the schematic. This yellow one shows the LEDs. It's mounted on a small circuit board. The blue one should show the glass plate, and upon the glass plate there are diffuser foils, and after the diffuser foils you have a homogeneous white light, and this goes into the LCD module, which makes then the picture. Here below you see a photo of this. So here you see the LEDs, these bright dots here, and the small dots, this is the front of the light guide. The light guide has mirror foils on the rear side and on the top, and only small dots are not mirrored. And these small dots let the light out to the front. The dots are smaller the closer they are on the LEDs, and bigger the farther away they are, because LED is only on one side, and higher intensity is here, smaller dots let out the same quantity of light than bigger dots with lower intensity on this side. So the dimension of the dots makes the homogeneous light on the screen. But you don't want to see dots. That's why diffuser foils are used. In this display it is 3 diffuser foils, and these foils make, let not see the dots, but make a very homogeneous surface on the screen. So this is the principle of this LED backlight. Advantage is low energy, of course. It's very thin, much thinner than the direct backlight unit, very low in weight, and it also has a very good price-performance ratio. So we are currently at the time that the LED panels come into the same range of cost than the former CCFL displays. They come into the same performance. So now is the time in this year 2011 where there will be the big switch in the market from CCFL to LED backlight. We are already realized a lot of displays in quite all over the lines. The only ones that do not have LED backlight at the moment are the 24 and the 27 with IPS panel, because here still the performance and also the price is not good enough. So CCFL still has some advantages, but we expect LED to be ready to be used also in these displays in about 1 year. So we are already investigating in new models that bring LED also in these large sizes. To be complete, there's also another kind of LED backlight. Just want to mention this. It's called RGB backlight, and this one uses not a wide LED but small LEDs of the basic colors, and these are not edge type but on the rear side. This technology is very high-end in color, so the color of the backlight even can be adjusted. So it is used, for example, in film production companies, but it uses a lot of these elements, so it's very expensive, it's very high, it draws a lot of current also because of these many LED modules, and you need the distance here. So the height is quite thick, it's even more than 4 centimeters thick. One example of a monitor who uses this one is the HP Dream Color. This is a 24-inch monitor with an end-user price of about 2,000 euros. So film production companies doesn't take care, they need it, but you don't need it on your office desk, and the people for their home use, they really think about paying 2,000 euros or paying maybe 400 euros for a very good LED backlit 24-inch monitor. So this was the part about the panel. So now I will come to some items that are not panel related but also quite important for the display. For example, the interface. So the resolution of the displays is getting higher and higher. VGA, DVI interfaces, which are common, often are not good enough to support the resolution. That's why mainly 2 DisplayPort interfaces coming up more and more, especially in professional displays. And just here on this slide, I want to compare with HDMI, because some already asked me, why don't we use HDMI? Why don't we use only DisplayPort? Why do we need both? Both interfaces have one advantage, a big advantage of a small connector. So much smaller than VGA and much smaller than DVI. So the advantage is you can bring it on a notebook, you can bring 4 DisplayPort connectors on a workstation graphic card. So this is a big advantage, especially on the PC side. HDMI interface, you cannot lock it. You only simply put it in the socket, can tear it out again, but it is not locked. DisplayPort has these small hooks, so it is really interlockable, which is important. For example, in professional use, if you have high adjustable screens, you put it on, you put it up, and it can tear your interface out of the screen, but it's not possible with the HDMI. This is already a feature that's going more in the professional applications. Another thing is, the common support of resolutions. So most graphic cards that support DisplayPort go up to 2560 by 1600, which supports, for example, Quad HD resolution on upcoming 27-inch monitors or even 30-inch monitors. While HDMI, also if theoretically bandwidth-wise it's possible to support higher resolutions, most graphic cards, most displays that use HDMI focus on Full HD, which is 1920 by 1080 resolution. You hardly find support of a higher resolution. So this is really focused on entertainment applications. With HDMI, you can connect Blu-ray players, set-top boxes to your TV, to your display at home, while in the professional applications, workstation and so on, DisplayPort is coming up more and more on workstations. It's already quite a standard. And also on our notebooks, more and more DisplayPort notebooks are coming up. We need both. So for monitor side, it's not so good. We have to take care of both. So we bring DisplayPort on the professional side, on the premium, on the business lines, while we use the HDMI on the entertainment side, which is the SL line. Here you find more details. I only want to pick up a few of them. For example, with a DVI-D interface, which is the last line here, you could drive a 24-inch. So a little bit more resolution, but it's enough for a 24-inch. You cannot come up to 30-inch or 27-inch. Therefore, you need dual-link DVI, which is mainly restricted to workstations, but not common on standard PC. HDMI, as I already told, theoretically you can drive higher resolutions, but normally only Full HD is supported. DisplayPort, even with currently we use the 1.1, the first one, it's no problem to support 30-inch or 27-inch Quad HD resolution. And you can even, with the next generation, you can even use up to 2 of these large sizes or 4 of the 24-inch displays. So this is the future higher resolution monitors with the DisplayPort interface. So let's have as next a short view on response time. I already mentioned it when I compared the different technologies. These funny pictures, the quite old ones, so the numbers here are not actual, so they are not, there are lower numbers currently possible, but the principle is the same. You switch from a departure grayscale, for example, from totally white to another grayscale. And depending on from which grayscale you switch to another one, the times can be very different. So on modern displays, between white and black, it can be lower than 1 millisecond, but between black and a dark grayscale, it can be up to 20 milliseconds. So a huge difference, and this can cause smearing picture in moving pictures, or even can cause color changes in moving pictures. Overdrive technologies, and you will see on the next slide how it works, has one big task to bring, no matter from which grayscale to which one you switch, all in about the same range. So values that we realize now is about 3 milliseconds in the SL line and about 5 milliseconds in the premium line. These are the values that we can reach at the moment. How does it work? Without overdrive, the red line shows the voltage on the pixel. So switch from dark, for example, to bright. The voltage switches very fast. However, the LCD modules follow slower. And they follow slow, and also the brightness of the dot is following slower. What does overdrive make? Overdrive makes an additional voltage peak at the beginning, which makes the LCD module switching fastest, and when they reached the target, they switch again to the target voltage, and the same switching back again. It's similar like driving with a car. If you want to go faster, you press your gas you press it more, and when you reach your target speed, you reduce it again. The same principle is also used with the overdrive technology. And this brings advantages in moving pictures, especially in the premium line, when you move fine drawing graphic renderings, for example, with very small differences in the color, then you need this overdrive to prevent color changes in the moving picture. So now coming to the last slide of my presentation, and this should explain how can you reach millions to one contrast with LED backlight. So let me first start with the common interpretation of contrast in the lower part of the picture, which is the static contrast. That means you measure a bright point when the brightness of the display is blown up on 100%. So normally it's 250 candelas, which is the maximum brightness. To get the contrast, you also need the darkest possible point. I have to say the contrast is always measured in a total dark room. So this contrast you never see in this office environment because you have already environmental light. But it's very difficult to take in consideration also the environmental light. That's why it's common to measure contrast in a total dark room. In a total dark room, the most dark point with same brightness of the backlight is, for example, in this example, is quarter of a candela per square meter, and the contrast is you divide the maximum by the minimum, so you get a typical value of 1,000 to 1, which is really a typical value for static contrast in quite all of the panels that are available on the market. So this is important for static pictures for office applications, for example. What is now dynamic contrast, or we call it advanced contrast rate? There is a circuit in the display, and this circuit looks at the average brightness of the screen content. So if the screen content is very bright, it switches the backlight to the maximum. Maximum cannot be higher than maximum brightness, 250 candela in this example. If now you have a very dark scene on your movie, it's reducing the backlight, and you measure the darkest point in the most darkest scene you can imagine, and so you can reach very low value. LED can be reduced, the brightness of LED can be reduced quite to zero. In former times with CCFL, this was not possible. CCFL, if you reduce it, there is a limit, and then it suddenly stops lighting. So on CCFL, the limit was in the contrast of about 50,000, 80,000 to 1. On LED, it goes quite to zero, so you can theoretically make infinitive contrast. Currently, the values are, it makes sense to give values of some millions to 1. There are already some competition that make 12 millions or even higher one. So theoretically, you can make infinitive numbers here. However, you don't see anything anymore because the backlight is turned to black and you do not see anything anymore. But it's a value that everybody sees. The higher the contrast, the better it is. And so we write contrast of about 2 million or 5 million in the data sheet. And it's only applicable in moving pictures, in changing content of pictures. It is even recommended to switch it off in office use, because otherwise, if you, for example, mark some Excel columns, they get dark, and then suddenly the whole picture is getting dark, and this causes unwanted flickers on the picture, which is really not ergonomic in office use. So it is recommended to switch it off, and we switch it off if you select office mode on the display. Yeah, this was my light slide, so I'm at the end of the presentation. I hope it was a little bit interesting for you, and I want to give back to the moderation for the question and answer session. Thank you.
Thank you, Stefan. Ladies and gentlemen, for your questions on the phone, simply key star, then 1 on the telephone, record your name at the prompt, then press the hash key. Once again, star 1, record your name, press the hash key. You may also submit question on the web by clicking on the Q&A on the top of the screen, typing in your question, and clicking on the Ask button. All questions will be answered in order received. And I think we've got a question already, and it's coming from... There's no name recorded, so caller, your line is open. Please go ahead.
From Hebron.
Yes, please go ahead.
Sorry, I didn't understand something.
En som inte har förstått någonting.
I'm sorry, I do not understand. I can't hear something.
The caller, your line is still open. If you want to ask a question, do so now. All right, just going to close the line again. Once again, ladies and gentlemen, star 1, record your name, press the hash key for your questions on the phone. There's still no questions, Stefan. Once again, ladies and gentlemen, star 1 for your questions on the phone, or type in your question on the question answer box on the live meeting screen. Click on the Ask button for your web questions. Okay, Stefan, we have no questions at this time.
Am I on the line?
Yes, sure.
Okay. Sorry, didn't catch it. Yeah, no question. Then thank you very much for your attention. You know how to reach me, so if you have questions later on, please ask me. Thank you for your attention, and wish you a nice evening. Goodbye.
Thank you, Stefan. Ladies and gentlemen, this concludes your conference call. You may now disconnect your lines. Have a very good evening. Thank you. So, Stefan? Yeah, was everything okay?
Everything okay. There's just music in the background. I can't understand you very good.
Yeah, sorry about that.
Okay.
Was everything okay?
Yeah, it was okay for me. Yeah.
Okay, was everything okay from my side? We had about 12 participants.
Okay.
And the recording and list will be ready tomorrow.
Okay.
Okay.
Yeah. Thank you very much.
Thank you. Bye-bye.
Bye.